Hey guys, in this video we're going to learn a little bit about the basics of Gauss's law. To start with, this is Gauss's law. Each side of the equation here represents electric flux. This symbol right here is in fact electric flux. Don't worry about exactly what that is in a moment. I'm just defining my terms. So that means that E times A is flux, and Q enclosed over epsilon naught is also electric flux. Writing that a little nicer as a fraction, that's this. Epsilon naught, if you recall, is a constant from earlier in the packet. It's 8.85 times 10 to the negative 12. So tiny, tiny little number. It's called the permittivity of free space. All right, that name's not important, but just so you know, that is what it's called. All right, so what is Gauss's law used for, and then what is electric flux would be the next things. So let's start with what are we going to use it for? Fundamentally, its utility is it's a great way for you to find electric field. That's really what we're mostly going to use it for, is finding the electric field due to a variety of different shapes. Those shapes would be really just three different things. We have the sphere. That's a really terrible sphere, but just bear with me. All right, sphere, the cylinder, and a plane. That's it. Those are the things that Gauss's law can conveniently find the electric field for. So if there's a charged sphere and you want to find the field inside of it somewhere or outside of it, out here, Gauss's law can do that. If you want to find it inside or outside of a cylinder, Gauss's law can do it. Above, below, inside of a plane, right? Gauss's law can do that as well. So those are the only solids that we are ever going to use Gauss's law for, though, practically speaking. That being said, the book is going to ask you a number of, frankly, relatively wonky questions. And those are going to be questions that look, something like what you'll see down below here. This is example 9 from your notes packet. They're representing here a pretty common, simple Gauss's law scenario where you have an electric field, that's represented by the arrows there, going through some kind of a solid, particular orientation, all right, and then they want to know things like the flux through the back face, the flux through the front face, right? In this case, specifically, it wants you to show that the flux through the back and the front is equal and opposite. Well, okay, that's going to require us to talk a little bit about the two sides of Gauss's law. So the left side is what we're going to address first with this question. In the left side of Gauss's law, you've got, all right, the electric field magnitude, the surface area vector for each of these various faces, and then there's a dot in there, which you would maybe assume from, previous is just a multiplication dot, but no, because this is physics, that's a dot product dot. Okay, so flux then is E times A times cosine theta. All right. Now, there's a few different things to discuss here. One would be A is not actually just the surface area of a particular face. If I wanted to know the flux, for example, through the bottom, I mean, you can't really see the bottom, but you intuit that it exists. If I said, what is the flux through the bottom face here? The correct answer would actually be 0. It wouldn't just be 50 newtons per coulomb, because that's the electric field, times whatever the surface area of the bottom is. No, it would be 0. And the reason it would be 0 is because of the way that we define A and theta. A is what's called the surface area vector. It might seem silly to have a vector for a surface area, but it's necessary for things like this. The way a surface area vector works is if you've got a face to some kind of a solid, the surface area vector points out from the solid at the center of that face or surface, however you want to define that. So like for the back face then, that means the surface area vector points directly to the left. For the bottom face, the surface area vector is pointing straight down. For this sloped face, the surface area vector would be something like that, right? Perpendicular to the side. All right, and then the front and back, the two triangular faces, I'm not going to try to draw those. Would be coming straight towards you and straight away from you. All right, the surface area vector for the bottom face being straight down and these electric field lines going directly to the right give you an angle theta of 90 degrees. So the flux through the bottom is 0 because cosine 90 is 0. Said another way, you can think about flux as being more or less proportional to the number of field lines that go through a surface. Okay, what does that mean? Well, the flux isn't the number of field lines that go through a surface. For example, I can't just count 1, 2, 3, 4, 5 and say that's the flux, it's 5. See? It's proportional to the number of field lines that go through a surface. The reason I'm saying it that way is because it helps you to understand why there's no flux through the bottom. If the lines don't actually go through the surface, meaning these ones really just like at best kind of brush over the surface, then there's no flux. Okay, now let me back up for a second. What is flux in the first place? I don't really need you to think too hard about that. Flux is always the product of some kind of a field times the surface area. There's many different kinds of flux, mostly electric flux and magnetic flux, and they're always field strength times surface area. What does it mean? Well, it's a mathematical quantity. It's not a physical thing that you could say put in a box or even like measure with a meter or something, right? There's no device that measures flux. It's always a calculated quantity. And it's proportional to the number of field lines that go through a surface. All right, therefore, there's no flux through the bottom face of the triangle. All right, there's also no flux through either of the triangular faces because no lines actually go through it. So for this particular case, there's only flux through the backside, and there's flux through this sloped side. All right, now, to get the flux through each of those sides, all you would really need to do is this. The flux through the back face would be 50 newtons per coulomb times the surface area. Let's see, it says that it's 1.5 meters tall and 0.2 meters deep, meaning that's this dimension. 0.2 by 1.5, and the field is 50, so there you are, whatever 50 times 0.2 times 1.5 is, times cosine of, brace yourselves, 180. What? Why 180? All right, well, let me go back to when I drew that surface area vector previously. Remember, it goes out of the solid object. Okay, drawing that arrow there, you should be able to see that since that arrow and the electric field arrows are in exactly opposite directions, that's going to be 180 degrees. Right? Therefore, we use cosine 180. A simple rule, though, is if the lines go in, meaning if the field lines go into the solid, that is negative flux. There's actually a reason for that we'll discuss in a little bit, but for right now, it's just the rule. If the lines go in, then that's negative flux. If the lines go out, that's positive flux. Okay, so we could multiply that all out, and we get 15. 15 what exactly? Well, that's a great question. Let's ponder that. Looking at the equation for flux, it's E times A. Electric field, you ought to know, is measured in newtons per coulomb. And surface area is measured in square meters. So that means our units would be Newton meters squared per coulomb. That's it. You would never, ever need to memorize the units for flux. Okay, just it's a thing where if you need it, you're going to look at the formula, E times A, and figure it out. That's it. Don't memorize it, just figure it out from the formula. Okay, next, the sloped face. I'm going to kind of gloss over how we do the sloped face, because here's the thing. We would, try to figure this side out using trigonometry and come up with that and the new surface area of that side. And here's the thing. This surface area is actually just going to be larger by a factor of 1 over cosine theta. So this area is the area of the left side divided by cosine of, it says the slope's 37 degrees. So when we get to the stage where we have to multiply by cosine theta, that difference in area is going to exactly cancel out by that angle right there. So it's a larger area, but we get the same amount of flux because of the angle at which those lines go through. So there's exactly 0 difference between the flux through the backside, or the left side, and the flux through the sloped right side, because of the angle at which those field lines go in. So we'll just get, oh, I'm sorry, I messed something up earlier. There, negative 15 should have been our answer to the flux through the left side. So the flux through the right side then is just positive 15. And now there's if we go back to a couple of our rules for how we could have got that, look, we said flux is proportional to the number of field lines that go through a surface. If I've got the same number of lines going in, 5 lines going in as going out, then that means I must have the same amount of flux through that face, regardless of the angle or the proportions or anything else. If the same number of lines go in as go out, then the flux is the same. And it's positive because of this rule, the lines are going out. Okay. So that's one of the major kinds of flux questions, is they're going to give you solids like this, and pretty much it's just going to be E times A. Occasionally you might have to worry about an angle. More commonly, though, you'll get these questions. These questions where you've got a charge and a couple of different what are called Gaussian surfaces drawn around it are the other major type of Gauss's law question. And they focus on the right side of Gauss's law, which says that flux is also equal to Q enclosed over epsilon naught. So that is also flux. These questions are maybe a little bit of a weird thought experiment, but that's essentially what they are, is a thought experiment. You are imagining a Gaussian surface, which is just to say a surface of whatever the heck shape you want, drawn around a charge of some kind, or maybe drawn near a charge, whatever, just drawn anywhere you like, because it's imaginary. You can do anything you want with that Gaussian surface because it's imaginary. Train of thought. Okay, it was drawn around a charge. Okay, and then they're going to ask you things like the flux through the various surfaces here. Okay, well, all right. Essentially, all you got to do when you want to find the flux through, like, say, this surface or that surface is say, Q enclosed over epsilon naught, how much charge is inside of that surface, inside of that sphere? Well, the answer is, it would appear, plus Q. So that's it. Q over epsilon naught. Ding, 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 we have a winner. That is the flux through both of these spheres, because they enclose the exact same amount of charge. That's literally the entire question. Okay, it's how much charge is inside of that Gaussian surface, and that's it. Q over epsilon naught is the flux. It's that easy. All right, now B wants to know, what if we drew a cube around it? Oh my gosh, it's a cube now. What could this mean? Well, if it's a cube, still same thing, right? The flux is not any different, still the same thing, because I'm enclosing the same amount of charge. All right, now with a cube, they can ask other questions, or some other shape, like a tetrahedron or something. They can ask other questions like, what's the flux through each face? Those ones, in theory, can get weird, but as long as the charge is in the middle of the cube, it's just going to be an equal amount of flux through each face. And so you would just say for each face of the cube, since they've got 6 faces, Q over 6 epsilon naught. All right, now I want to make sure everybody understands a little bit why the answer is what it is, because sure, yes, you can just remember Q enclosed over epsilon naught, but remember the rule was that the flux is proportional to the number of field lines that go through a surface. So if I draw a few of the field lines coming off of this, right? Can't draw them all because there's technically as many as you feel like drawing. You can see that the same number of lines go through each of those two surfaces. Or even if it's cube, same number of lines go through each of those faces, right? And so it's the same amount of flux because it's the same amount of charge enclosed, but also since flux is proportional to the number of field lines, we've got the same amount of flux through each of those two surfaces. All right, now, the only wrinkle that they can throw at you is something like this. Here's a charge. All right, let's say it's Q. And then you draw a Gaussian surface around it. Okay? And then over here is a minus Q. And they say, what is the flux through the Gaussian surface? If you're looking at that and you're like, I don't know, the minus Q over there seems important, right? They wouldn't have mentioned it if it weren't important. Nobody cares. Gauss doesn't care. Gauss says, is it enclosed? Because that's what Q enclosed means. Oh, if it's not enclosed, nobody cares. So it's the same. It's the same amount of flux because that minus Q isn't even inside of the Gaussian surface, so we don't care. All right, now, if I draw another Gaussian surface, such as this one, it's like a rectangular prism or something, that one is enclosing the Q and the minus Q. And so we do care now. And the net flux through that surface would actually be 0 because for my green surface that I drew here, Q enclosed is, in fact, a grand total of 0. So there would be flux through various faces on it, but the total would work out to be nothing at all. All right, that should be enough of an introduction. All the various questions that you're going to see in this first homework are going to boil down to some variation on those two major problem types. So if you get stuck, just look back at the rules that we've outlined here.